Everything we thought we knew about how black holes are born is probably wrong. That is not a headline. That is the conclusion of 3 independent research teams at Cambridge, Harvard, and Yale, working with different data from the same telescope, arriving at the same answer. Supermassive black holes did not grow slowly from dead stars over billions of years. Some of them were already there, massive, ancient, waiting in the dark before the first star in the universe had even begun to shine. And the James Webb Space Telescope has finally seen them. To understand why this is not just another discovery, why it shakes the foundation of how we model the universe, you need to picture what the Webb actually does. It does not fly to distant galaxies. It sits at a gravitationally stable point called L2, 1.5 million kilometers from Earth, perfectly still, shielded from the sun by a membrane the size of a tennis court that cools its instruments to -233 degrees Celsius. At that temperature, the telescope becomes sensitive to infrared light so faint that it has been traveling across the expanding universe for over 13 billion years. Every photon it catches is a message from the deep past. The deeper it looks, the further back in time it sees. Not metaphorically, literally. Light from an object 13 billion light-years away left that object 13 billion years ago. The Webb is a time machine that works by waiting. And when it trained its 6.5-meter gold-plated mirror on the Abell 2744 galaxy cluster, one of the most massive gravitational lenses known, using the cluster itself as a natural magnifying glass to peer even deeper into the background universe, it found something nobody had predicted. Scattered across the image, almost invisible among thousands of galaxies, were dozens of tiny red objects, compact, faint, completely absent from every survey ever made by Hubble or any ground-based observatory in 30 years of deep-field imaging. Astronomers started calling them little red dots. It was a casual name, almost dismissive, a placeholder until someone figured out what they actually were. But nobody could. They were too small to be normal galaxies, some only a few hundred light-years across, when a typical galaxy like the Milky Way spans over 100,000. They were too red, suggesting thick shrouds of gas and dust absorbing and re-emitting light at longer wavelengths. And they were far too bright for their size, radiating energy at rates that no known stellar population could produce in such a small volume. For months, no model could explain them. Teams at multiple institutions tested every hypothesis: young starburst galaxies, dusty quasars, unusual stellar populations created by exotic initial conditions. Nothing fit cleanly. Every model left residuals that could not be ignored. And then the spectra came in. More than 80% of these little red dots showed gas spiraling at over 1,000 kilometers per second. To put that in perspective, a bullet travels at roughly 1 kilometer per second. This gas was moving 1,000 times faster, in tight orbits around something extraordinarily massive and compact. Gas does not reach those velocities unless something with immense gravitational pull is dragging it inward. These were not galaxies in any traditional sense. They were feeding grounds. Something at the center of each one was swallowing matter at a rate that should not have been possible that early in the history of the universe. Some of these objects appear to date from just 600 million years after the Big Bang. The universe at that age was supposed to be a quiet, diffuse place, still assembling its first generation of stars from cooling hydrogen clouds. Instead, the Webb found monsters already at work, already gorging, and that was only the beginning. In February 2026, Fabio Pacucci, a staff astrophysicist at the Harvard-Smithsonian Center for Astrophysics and a researcher at the Black Hole Initiative, published a paper that reframed the entire conversation. His team had spent months analyzing the spectral signatures of the little red dots, cross-referencing their emission lines, their luminosities, and their compact sizes with every known model of early universe objects. Starburst galaxies did not fit because the energy output was too concentrated, too uniform, and lacked the telltale signatures of massive young stars. Standard active galactic nuclei did not fit either, because the X-ray emission was bizarrely weak, orders of magnitude below what a normal quasar of that luminosity should produce. The little red dots were screaming in infrared, but whispering in X-rays, and that combination ruled out every familiar category. The conclusion Piccucci arrived at was direct and unsettling. These are accreting direct collapse black holes. Not black holes that grew from the remnants of dead stars over billions of years. Black holes that formed from enormous clouds of primordial gas collapsing straight into a singularity, without a star ever existing in between. The paper was posted to the archive in January 2026 and immediately drew attention from the global astrophysics community. Let me be specific about why that sentence carries the weight it does. For decades, the textbook story of black hole formation has followed a clean, satisfying sequence. A massive star is born from a collapsing cloud of gas and dust. It burns through its hydrogen fuel over millions of years. When the fuel runs out, the core collapses under its own gravity. If the original star was massive enough, somewhere above 25 solar masses, the collapse produces a black hole. That black hole typically weighs between 10 and 100 times the mass of the Sun. That is your seed, a tiny gravitational anchor sitting in the ashes of the star that made it. From there, the seed grows. It pulls in surrounding gas, forming an accretion disk that spirals inward, heating up to millions of degrees, radiating energy across the electromagnetic spectrum. But there is a speed limit on this process. It is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who calculated it in 1926. It is the maximum rate at which matter can fall into a black hole before the radiation produced by infalling material pushes incoming gas away. Think of it as a balance point between two forces. Gravity pulls gas in. Radiation pressure pushes it back out. The black hole can only eat so fast before its own meal fights back. This limit means that even under ideal uninterrupted conditions, a stellar mass seed of 100 solar masses needs billions of years of continuous feeding to grow into a supermassive black hole weighing 1 billion suns. The model is elegant. It is internally consistent. It matches everything we observe in the nearby mature universe. And it cannot explain what the Webb is seeing in the distant, young one. The universe is 13.8 billion years old. The Webb is finding supermassive black holes, some weighing hundreds of millions to billions of solar masses that already existed when the universe was less than 700 million years old. That is 5% of the total age of the cosmos. Run the maths. Start with a seed of 100 solar masses. Let it accrete at the absolute maximum Eddington rate, continuously, with no interruption, no merger delays, no periods where fuel runs dry or gets blown away by feedback. It still does not reach 1 billion solar masses in 700 million years. The clock runs out before the black hole gets big enough. The numbers do not close. Something else had to be happening. Something that skipped the first step entirely. In 2025, Roberto Maiolino, a professor of experimental astrophysics at the University of Cambridge and one of the most published researchers in the field of high redshift galaxies, pointed the Webb at a specific object lurking behind the Able 2744 galaxy cluster. It had been detected earlier during the Uncover survey, a program designed to use the cluster as a gravitational lens, and was initially catalogued as QSO-1. Just another little red dot in a growing census. But something about its spectrum nagged at Maiolino. The hydrogen emission was unusually clean, too clean. He requested dedicated spectroscopic time on the Webb, hours of precious telescope observation focused entirely on this single object, drilling deeper into its chemical composition than any previous measurement. What came back stopped the conversation. QSO-1 is a black hole weighing approximately 50 million solar masses. That alone is not what made headlines. 50 million is large, but our own galaxy hosts a black hole of 4 million solar masses, and the nearby galaxy M87 harbors one of 6.5 billion. What is remarkable, what made Maiolino use the word that would define the discovery, is what surrounds it. Almost nothing. No visible host galaxy. no population of surrounding stars, no complex chemistry of any kind. The gas in the immediate region is composed almost entirely of hydrogen and helium, the two simplest elements in existence, the ones that were synthesized in the first 3 minutes after the Big Bang during primordial nucleosynthesis. There is no carbon, no oxygen, no silicon, no iron, no nitrogen, no neon. Every one of those heavier elements, everything astronomers collectively call metals, regardless of whether they are actually metallic, is forged inside the cores of stars through nuclear fusion and scattered into space when those stars explode. Their complete absence in the region around QSO means one thing, and it is an extraordinary thing. No star has ever lived or died there. Maiolino called it a nearly naked black hole. The phrase stuck, not because it is poetic, but because it captures exactly what makes this object so deeply disturbing to every existing model of cosmic structure. Here is a black hole 50 million times more massive than the Sun, sitting in a chemically pristine environment 700 million years after the Big Bang. If stars had formed in that region first, even a single generation of them, there would be metals, even trace amounts. Supernovae are not subtle events. They scatter enriched material across thousands of light years. If stars had died anywhere nearby, the forensic evidence would be unmistakable. There is none. This black hole did not form from the death of a star. It did not grow slowly from a small seed fed by stellar winds and gas recycled through generations of stellar birth and death. It existed in a universe where stars had not yet polluted the gas around it with their chemical signatures. It is not just old. It predates the very process we thought created black holes in the first place. And it gets stranger. QSO-1 is not alone. Dozens of similar objects have now been identified across multiple deep fields observed by the Webb. Each one is too massive, too early, and too chemically isolated for the traditional model to accommodate comfortably. They are not anomalies that can be explained away as individual oddities or measurement errors. They are a population, and populations demand a mechanism. This is where the story takes a turn that most documentaries skip entirely, because the natural instinct, the dramatic instinct, is to treat the traditional model as the villain of the new one, as if the old theory was naive, lazy, or simply wrong from the start. It was not. The model that says black holes are born from dead stars was built on decades of painstaking observational physics. Stellar evolution is one of the most tested and confirmed frameworks in all of astrophysics. Every stage of it has been observed. Stars are born from collapsing molecular clouds of gas and dust. They ignite hydrogen fusion in their cores. They spend millions or billions of years on the main sequence, depending on their mass. When the hydrogen runs out, they fuse helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. And when the iron core reaches the Chandrasekhar limit, approximately 1.4 solar masses, no further fusion reaction can release energy. The core collapses in milliseconds. The outer layers rebound outward in a supernova explosion that briefly outshines an entire galaxy. What remains at the center is either a neutron star, or, if the original star was massive enough, a black hole. That sequence is not theoretical speculation. It is observed, measured, and confirmed across thousands of stars in our own galaxy and in neighboring ones. The problem was never with the physics of how stars die. The problem was with the assumption, rarely questioned because it seemed so natural, that this was the only way to build a black hole. That every black hole in the universe, from the smallest to the most supermassive, must trace its origin back to a star that once shone. For a long time, almost nobody questioned it seriously. Almost nobody. In 2006, an astrophysicist named Priyamvada Natarajan, working at Yale University and later affiliated with the Black Hole Initiative at Harvard, proposed an alternative pathway that cut through the timing problem with a single powerful insight. She called them heavy seeds. The idea works like this. In the early universe, before the first generation of stars had formed, there existed enormous clouds of pristine gas, tens of thousands of solar masses of hydrogen and helium, with no metals to cool them efficiently. This detail about metals is critical. In modern star-forming regions, metals and dust act as radiative coolants. They allow gas to shed energy quickly, contract, fragment into smaller clumps, and form individual stars. But in a pristine, zero-metallicity environment, cooling is extremely inefficient. The gas stays hot, stays pressure-supported, stays turbulent, and resists breaking apart. Under the right conditions, in regions of high enough density and low enough angular momentum, the entire cloud can collapse inward as a single object, not into a star, directly into a black hole. A black hole weighing between 10,000 and 100,000 solar masses from the moment it forms. No star required, no supernova, no Eddington limited crawl from 100 solar masses. With a starting mass of 100,000 suns instead of 100, reaching 1 billion solar masses in 700 million years is not just possible, it is comfortable. The timing problem dissolves completely. Natarajan's theory was elegant and physically motivated. It was also, for nearly 2 decades, unverifiable. No telescope existed that could see these objects. Hubble could not peer far enough into the infrared. Ground-based instruments were blinded by atmospheric absorption at the critical wavelengths. Natarajan published her papers. She refined her models with collaborators. She presented at conferences year after year. And the broader field moved on, because without observational confirmation, a theory remains a theory no matter how beautiful its mathematics. Then the James Webb Space Telescope turned on, and the data came. In July 2025, Peter van Dokkum at Yale University and Gabriel Brammer at the Cosmic Dawn Center of the University of Copenhagen published something that read less like a standard astrophysics paper and more like a crime scene report. They had been studying a pair of colliding galaxies nicknamed the Infinity Galaxy, observed by the Webb during a systematic survey of galaxy mergers. The two galaxies were in the process of smashing into each other at tremendous velocities, their nuclei still visible as 2 distinct bright spots, each surrounded by a ring-like structure of disrupted stars. But between the 2 merging nuclei, suspended in a vast, turbulent cloud of compressed gas, sat something that had no business being there. A black hole weighing approximately 1 million solar masses. It was not located inside either galaxy. It sat between them, floating in the collision debris of 2 worlds, tearing each other apart. The velocities told the story, and they told it clearly. Van Dokkum's team measured the motion of the surrounding gas cloud and the motion of the black hole independently using precise spectroscopic data from the Webb. They were moving at nearly the same speed, within about 50 kilometers per second of each other. To appreciate what that means, consider the alternative. If the black hole had been ejected from one of the galactic nuclei during the merger, its velocity would differ dramatically from the gas. It would be a bullet passing through a cloud. Instead, the black hole and the gas were co-moving, like 2 objects that had always been part of the same system. When an object and the material surrounding it share nearly the same velocity, there is really only one plausible interpretation. They formed together. This black hole was not captured from one of the galaxies. It was not flung out from a galactic center by a 3-body gravitational interaction. It was born directly from that gas cloud. The collision between the 2 galaxies had compressed the gas in the overlapping zone so violently that it skipped the entire process of star formation and collapsed directly into a black hole. The team estimated that the initial collapse may have produced a seed of roughly 300,000 solar masses, which then grew to its current mass of approximately 1 million suns over a period of about 50 million years. The growth rate was rapid, but within known physical limits. Direct collapse, caught in the act. Not in the primordial universe 13 billion years ago, where direct observation is barely possible, but in a galaxy merger that happened roughly 50 million years ago. Close enough in cosmic terms to study in extraordinary detail. Close enough to measure velocities, gas compositions, and spatial relationships with precision. This is the discovery that transforms the entire theory from an elegant hypothesis into an observable process. If direct collapse can happen now, in a relatively recent galaxy collision where conditions are extreme but not unique, then it could certainly happen in the early universe, where gas densities were far higher, temperatures were more extreme, and metals were entirely non-existent. The infinity galaxy is not a fossil from the primordial cosmos. It is a living laboratory. A process that was theoretical for 20 years, debated at conferences, modeled in supercomputer simulations, and quietly doubted by skeptics who demanded observational proof, is now something that astronomers can physically point to and say, there. It happened there. We measured it. 3 teams. 3 independent discoveries. Little red dots identified as accreting direct collapse black holes by Pacucci at Harvard. A naked, starless black hole in chemically pristine gas found by Maiolino at Cambridge. And a direct collapse caught mid-formation between 2 colliding galaxies by Van Dockum at Yale. Each team used different data, each applied different methods, each pointed to the same conclusion, and the conclusion points in a direction that is genuinely unsettling. Because if supermassive black holes did not need stars to form, then the sequence we have taught in every astronomy textbook for half a century, the sequence that says the Big Bang produced hydrogen and helium, gravity pulled that gas into clouds, clouds collapsed into the first stars, stars forged heavier elements and died. Their remnants became black holes, and those black holes slowly grew and eventually anchored the centers of galaxies. That entire sequence might be running in the wrong order. The black holes may have come first, not as products of galaxies, but as the gravitational seeds around which galaxies eventually assembled. The first structures in the universe may not have been points of light. They may have been points of collapse. Matter falling toward an already existing gravitational well, gathering, condensing, and only then igniting the first generation of stars, not randomly scattered through space, but in orbit around something that was already there, already massive, already dark. That is not a fringe idea being whispered in speculative corners of theoretical physics. It is now being actively modeled by multiple research groups around the world using cosmological simulations that incorporate heavy seed formation as a standard channel alongside the traditional stellar remnant pathway. If confirmed by the next generation of observations, it rewrites the hierarchy of cosmic structure formation in a fundamental way. It means the first massive objects in the universe were not luminous. They did not shine, they swallowed. They were collapses, not ignitions, points where gravity won before light even had a chance to exist. And there is a deeper question that nobody has answered yet, one that sits at the uncomfortable boundary between astrophysics and fundamental cosmology. If black holes can form directly from gas in the first few 100 million years after the Big Bang, could some have formed even earlier? Could they have formed in the first fractions of a second, not from collapsing gas clouds, but from density fluctuations in the fabric of space-time itself? The universe in its first moments was unimaginably hot and dense. Any region that was even slightly denser than its surroundings could, in principle, have collapsed under its own gravity before the expansion of space could smooth it out. These would be primordial black holes, objects that predate not just stars, but atoms. Not born from any astrophysical process, but from the geometry of the Big Bang itself. Some physicists have proposed that primordial black holes could account for part of the dark matter, the invisible mass that constitutes roughly 27% of the total energy content of the universe, holds galaxies together, bends light around galaxy clusters, shapes the large-scale cosmic web, and has never once been directly detected by any instrument ever built. That idea remains firmly in the realm of informed speculation. Nobody is claiming it is true. But the fact that it is no longer dismissed outright, the fact that serious researchers at serious institutions are modeling it, running simulations, and designing observational tests for it, tells you how much the ground has shifted beneath our feet in just 3 years of web data. In September 2026, NASA is scheduled to launch the Nancy Grace Roman Space Telescope. Roman will not replace the Webb. It will complement it in a way that could break this question open. Where the Webb sees deep and narrow, staring at tiny patches of sky with extraordinary infrared sensitivity, Roman will see wide. Its field of view is 100 times larger than the Webb's in a single exposure. It is designed for surveys, for mapping the large-scale structure of the universe across vast volumes of space and time. If heavy-seed black holes are as common in the early universe as the little red dots suggest, Roman will find hundreds or thousands more. If primordial black holes exist and leave gravitational fingerprints on the distribution of matter across the cosmos, Roman is the instrument designed to detect exactly those subtle distortions. The question you carry home tonight is simple, and it has no answer yet. What came first in the universe, light or collapse? Did the cosmos begin by shining, or did it begin by falling inward? And if the darkness was already there, before the first photon, before the first atom, before the first second had fully passed, what does that tell us about the kind of universe we actually live in? Thanks for watching, and I will see you in the next one.